Hey everybody, this is Mr. Charnitsky, and this is Geometry Lesson 3, Unit 3. And the first thing I'd like you to do is take a look at this jump start. We have two figures here, one on the left, one on the right. And notice the difference between two. And what I'd like you to do is to jot down first briefly how we get figure 1, and then how do we get from figure 1 to figure 2? So go ahead and pause this video and work on that for a few moments. And when you're ready, go ahead and start the video and we'll go through the solution. Okay, so for the first figure, what we have here is obviously a perpendicular bisector. We know it's perpendicular because of the right angle, and we know it's a bisector because of the tick marks here and here. So we know that AB gets split in half. The only thing I'm going to do is let's add a name for our point in the middle. Let's call it point M for midpoint. So the starting figure is segment AB with line L as a perpendicular, that's a symbol for perpendicular, bisector. Okay. All we need to do to get the next figure is to first add point C, on line L, then connect segments AC and BC. All right. Next, we have this figure here again, and we have Tia and Tahani, and what they're trying to prove is that this point C on our perpendicular bisector is equidistant from A and B. In other words, ultimately we're trying to prove that these two segments are equal. We already know that we have this point M is the midpoint. We know we have this perpendicular angle, but can we prove? We can look at it visually and have good intuition that those two are equal, but we haven't quite proven it yet. Okay? And that's what we're going to undo. All right. So we have Tia's statements, and Tahani is basically taking these statements and shortening them into very compact symbolic notation, because we don't want to have to write a whole lot of stuff, and especially for writing proofs, we want to write very short statements. Okay, so we start out with what we're given. Okay, we have a perpendicular bisector, and we're trying to figure out a point that's equidistant, so we're just going to pick any point, call it C. That's just the given picture that we have. Okay. Next, we look at what we're trying to prove, and that is what I highlighted above. We're trying to prove that the distance that point C to the two endpoints is the same. Now, this next statement here is interesting. Instead of, just trying to directly prove that those two segments are the same, what we're going to do is we're going to look at the two triangles that we have here. And what we have on the two triangles is we have the triangle on the right and the triangle on the left, and we're going to try and see that they are we're going to try and see that, make the triangle on the right equal to the triangle on the left. And if we can prove that, then we would know that the two sides are congruent. Okay? So, some of the things that we know. We know that both triangles contain a right angle. Okay? So we have this angle right here. That's right, but there's also another right angle to the left of it. So both of them have a right angle. So we can say angle CMB is right, and angle should be a label CB and CMA. That's the one on the left. Okay. We know that the perpendicular bisector cuts the segment AB into two congruent segments. So we have the midpoint splitting this big segment into two equal parts. So we have two sides that are equal. So AM and MB are going to be equal. Obviously, this, the segment from C to the midpoint of segment AB is a side on both sides triangle. So they're talking about a shared side. So here's our shared side. So that gives us another side. Okay, so we'll say CM congruent to CM. All right. Looking at our two triangles, we have a pair of sides, and we have another pair of sides, and we have a pair of congruent angles in between. So by SAS, those two triangles are going to be congruent. So we can state that the two triangles, CBM and CAM, are going to be congruent. And since those two triangles are congruent, any of the parts are going to be congruent, so we can state what we're originally trying to prove, which was AC and CB are congruent. Okay. Thus, any point on the line L is going to be equidistant, because we can place C anywhere on that line. So this is still a pretty good long-winded proof with all of this writing. We still want to cut this big, lots of words here. We want to cut this down a little. We want to get a little bit more efficient with how we write things. So we're going to take this proof in the next step, and we're going to write it in a more easily readable, and something we call a two-column proof. Okay. So, in a two-column proof, you'll start with a given statement. Usually this will be written for you, so you usually don't have to write this. So, given segment AB with perpendicular bisector line L, prove any point C on line L is equidistant from A and B. Okay. And usually I'll have a picture. This usually is what's given to you. So you usually don't have to write this part on a proof. Start with AB. So that's what we're given. This is what we're trying to prove. We're going to organize this into a 2-column proof. On the left side of our columns here, these are our statements. And over on the right, these are our reasons. Every statement that we make has to have a valid reason. Our statements are essentially everything on the left column over here. And our reasons, we're going to shorten them up a little bit so not these long paragraphs. So the first statement is usually going to be our given. So we're just going to rewrite what's given up here. And again, usually you will have this provided. Okay, so your first statement, you'll usually have everything written here, and the black will be provided. So we're given segment AB with perpendicular bisector line L. Squeeze that a little bit. Put all one. And the reason we have that was given to us. Our next statement talked about we could talk about how we have, because it's a bisector, we have these two congruent segments, AM and MB. So let's go ahead and list those. AM is congruent to MB. The reason we know that is because L is a perpendicular bisector, so that's a definition of a bisector. It splits those into two equal parts. The next thing we looked at, we had two right angles. So angle CMA is right, and angle BMC is right. And how do we know that? Well, that's the perpendicular part, so that's the definition of perpendicular. It makes right angles. So there's our two right angles. Finally, we had our shared side right there. CM is congruent to CM. And rather as giving our reason as a shared side, our reason whenever we say something is equal to itself, we call that the reflexive property. Okay, so we have a pair of sides, a pair of angles, and a pair of sides. We've stated we know that they're congruent, so we can state that the two triangles are congruent. So triangle CAM is congruent to triangle BCM, or CBM, gotta make sure I'm putting this up, CBM, by SAS congruence. All right, and lastly, since we know the two triangles are congruent, we can say that CA is congruent to CB by CPCTC. Okay, corresponding parts of congruent triangles are congruent. Okay. So question 3. Would your justification be true regardless of where point C is chosen? No, it doesn't matter. I could put C up higher or underneath or anywhere on the picture. This proof will work out the same. So the proof does not need to specify where point C is. Okay, so this is a 2-column proof. It's a much more compact and organized way of looking at things than, say, a paragraph proof, but not necessarily a better way. It's just a more common way that mathematicians organize things. Okay, last questions here. You can use T and Tan's theorem about points on the perpendicular bisector of a segment to prove base angles of an isosceles triangle are congruent. Write a narrative proof for each of the following statements. Triangle ABC in T and Tahani's diagram is an isosceles triangle. Okay, so we know from our proof that CB and CA are congruent. Okay. We just proved it. Thus, triangle ABC must be isosceles. The base angles A and B of the isosceles triangle on Tahani's diagram are congruent. Well, that's the two angles on the left and the right. We already know the two triangles on the left and right are congruent, so that means any of the parts are congruent. So by CPCTC, angle A must be congruent to angle B because triangle CAM is congruent to triangle CBM. And finally, T and Tahani's diagram can be applied to all isosceles triangles. This is true because as we say before, point C can be anywhere on line L, and AB is not specified for any length. So we can make any isosceles triangle, and this will all be true. Okay? So we've essentially proven that the base angles of an isosceles triangle have to be congruent. Okay, let's go to the retrieval and do some practice problems real quick. So on the retrieval, we're just looking at our what method would we use to prove these triangles congruent. So go ahead and pause and try to answer these questions, and then you can check again when you're ready. Okay, number one, this would be side, angle, side. Number two, this would be angle, side, angle. Number three is side, side, side. And number four is angle, angle, side. For question number 5, in order to plot these reflection points, we have to be perpendicular to our line of reflection. So our line of reflection has a negative 1/1 slope. So our points need to have a positive 1/1, so we're just going to count steps. So it's 1, 2, so we'll do the 1, 2, down 1, down 1, down 1/1, so 1, 2, 3.5. One, 2, 3.5. Okay. Our last point. 1, 2, 3, 4.5. 1, 2, 3, 4.5. One, 2, 4. There we go. Half. Okay. And connect our dots. There's our reflected triangle. And our last one, we'll connect 2 points to draw the line of reflection and figure out the slope is going up 2/8. So I'm going to go halfway there, so I'm going to go up 1 and over 4. So there's where my line's going to go through the middle. And if we go up 2/8, that simplifies to 1/4. That's the slope of our line, of our corresponding points. Our line of reflection needs to be perpendicular, so I need to flip-flop that and make it negative. So this is going to go down 4/1. So from this point, it's going down 4 over 1. So there's our line of reflection, okay? And the slope is -4, and our y-intercept is right there at -2. All right. Good luck on your brace set goes, which are going to be problems up here. 1, 3, and 6 out of lesson 3. And I will see you next time.